Okay, welcome back everybody to the afternoon session, and the second talk of today's session will be by Gregory Moore from Rutgers on 2D categorical wall crossing and twisted maths with some application to knot invariants. So please go ahead.
Okay, well, thank you very much for the invitation. It's a pity I can't be in Rome and speak with you in person. So part of this talk is a review of old things, going way back, and also a review of some foundational material in a paper I wrote several years ago with Davide Gaiato and Edward Witten. And the new things are work I've been doing with my graduate student, Asan Khan, and he just graduated and will be going to the Institute for Advanced Study. At the end of the talk, if there's time, I forgot to turn on my timer. Let me do that. So 50 minutes, as I understand it, maybe 49 minutes. At the end of the talk, if there's time, I would like to tell you about some work in progress with Asan and Davide Gaiato and Fei Yan. Fei is a postdoc at Rutgers. She's very good and she's looking for a job. And that project came out of some broader discussions that involved Andy Knightsky and Tudor Damofta. So let's begin by recalling the relationship of supersymmetric quantum mechanics and homological algebra, which is nicely explained by thinking about the relation of supersymmetric quantum mechanics and Morse-Novikov theory. So to define a supersymmetric quantum mechanics, you introduce a Riemannian manifold M and a closed one form, Xi. Now, Xi is locally of the form dH, where H is a real valued function on M. That's what's traditionally used when defining superquantum mechanics. It's called the superpotential. But in this talk, H need not be single valued, so Xi need not be exact, and that will be important. We'll call Xi the super one form. So to form superquantum mechanics, your fields are a map. It's a 0 plus 1 dimensional field theory. The fields are a map from the real line of time into the target space M, the Riemannian manifold. The Lagrangian is the standard kinetic term, and the potential energy is the norm squared of Xi. So the classical vacua are at the zeros of Xi. I'll call those critical points. We'll assume they're isolated and non-degenerate in the sense that the mass matrix, this matrix of derivatives of Xi, is invertible. To each critical point, we can associate an approximate quantum vacuum. And you can calculate the fermion number of that approximate quantum vacuum, and it's half the number of the difference of the number of negative and positive eigenvalues of the mass matrix. It's well known that the approximate vacua are not exact because of instantan corrections. The instantan equation in this case is the flow equation defined by this one form Xi and the metric. So we use these instantons to define an operator Q on approximate ground states. The operator Q takes an approximate ground state of fermion number f sub I to the linear combination of all other approximate ground states of fermion number 1 higher, fi plus 1. And the way you weight the linear combination is by counting the number of solutions to the instanton equation. Now, these counts of instantons satisfy this identity here called the broken flow identity, which implies that Q squared is 0. So that means that we have a chain complex. So the chain complex has a vector space, which in our case is the span of the approximate ground states, and two linear operators on that vector space. One is called the fermion number in physics, or the homological degree in math. The other is the supersymmetry operator in physics, or the differential in math. And as we saw, Q raises fermion number by 1 and Q squared is 0. So in this particular case, I'll call it the MSW, Morse-Smale-Witten complex, and it depends on this data. Then Witten's main point was that the exact ground states of the supersymmetric quantum mechanics is the cohomology of this complex, which is the geometrically the cohomology with respect to the flat connection d plus psi. Now it's interesting to see how the MSW complex changes under homotopy. So we can consider a continuous family of the data that defines the superquantum mechanics, G and psi, where S is a control parameter, and these are continuous in S. And we ask, how does the MSW complex change? The answer is that you can define a linear transformation, U, from the complex at control parameter S1 to control parameter S2 by mapping all approximate ground states of fermion number F to the linear combination of all approximate ground states of the same fermion number at the other control parameter. Again, the linear combination is given by counting solutions of the instantan equation. Now it's a flow equation in the control parameter. By definition, U commutes with F, and then a non-trivial argument shows that U also commutes with the differential. So U defines what's known as a chain map. What I'm saying is that under continuous deformation of metric and super 1 form, the MSW complex changes by a chain map. But it's a very special kind of chain map. It's what's known as a homotopy equivalence of chain complexes. That will be an important idea for what follows. So if you have a homotopy of paths, a path of paths, that is a continuous map from the square into the space of metrics and super 1 forms, then at U equals 0, you get one chain map, and at U equals 1, you get another chain map. And you could show that the difference of those two chain maps is Q exact in the sense of this equation, where the operator E maps fermion number F ground states to the linear combination, the sum of all fermion number F minus 1 ground states. And again, you count the solutions by counting the number of instantons, the number of solutions to this flow equations. Now, in general, two chain maps are homotopic if there's a fermion number or minus 1 operator from V1 to V2, such that F0 minus F1 is Q exact in this sense. And if there are chain maps going both ways, so that the composition both ways is homotopic to the identity, we say that the chain complexes are homotopy equivalent. And homotopy equivalence of chain maps is an important idea for what follows. So let's apply these ideas now to quantum field theory in 1 plus 1 dimensions, the so-called 2,2 Landau-Ginzburg models. So to define the Landau-Ginzburg models, the basic data is a Kähler manifold with Kähler metric Gij bar and a 1,0 form alpha, which is holomorphic, d bar and alpha is 0. So again, locally, alpha is the derivative, the holomorphic derivative of a holomorphic function W called the superpotential, but we'll be considering multi-valued W. So we can formulate the action of the theory, here it is, in terms of just alpha. The dot dot dots are for fermions. This is a supersymmetric field theory. It is a 1 plus 1 dimensional relativistically invariant field theory. D is a spatial domain. If the spatial domain is the entire real line, then there are Poincare invariant vacua corresponding to all the zeros of this one form alpha. And because of supersymmetry, you can prove that these are in fact not only classical vacua, but exact vacua. Later we'll be talking about branes, and then the spatial domain will be the half-line. Now it's very useful to think of this supersymmetric quantum mechanics, to think of this 1 plus 1 dimensional quantum field theory as a supersymmetric quantum mechanics. The target space of this supersymmetric quantum mechanics is the space, calligraphic M, of all maps phi from the spatial domain D into the Kähler manifold X. The Kähler metric on X induces a Kähler metric on calligraphic M. Delta phi here means a cotangent vector on the calligraphic M. And similarly, alpha induces a super 1 form on calligraphic M, psi. And the value of the super one form at a field phi is, for example, is given by this equation. So just look at the first term. So omega is the Kähler metric, the Kähler form on the Kähler manifold X. You can pull it back and integrate over the one-dimensional spatial domain to get a one form on field space. Similarly, in the second equation, we're contracting alpha with delta phi. The virtue of this particular super one form is that if you go through the exercise of working out the action of the super quantum mechanics for this calligraphic M with this psi, you'll get exactly this action of the 1+1 dimensional quantum field theory, the Landau-Ginzburg model for X and alpha. Now, in the usual discussion of Landau-Ginzburg models, people assume that alpha is exact and W is a holomorphic and Morse function. If alpha has non-zero periods, then there's no single-valued superpotential. And in the physics literature, that's what's meant by the term twisted masses. It's a historical term. It's a little misleading. In this case, there exists an abelian cover, pi from x hat to x, so that if I pull back alpha, it becomes exact. And so upstairs, there is a well-defined superpotential, capital W hat. We'll let capital gamma denote the free abelian deck group and think of it as a subgroup of the first homology of capital X. So it's often convenient to work with the Landau-Ginzburg model upstairs and work equivariantly with respect to gamma. So we can denote the vacua upstairs by V hat equals phi, those are the points phi hat A, which are critical points of this well-defined superpotential, capital W hat. We can abbreviate the vacua phi hat A, B, and so on by A, B, and so on. And the action of the deck group on the vacua just shifts A to A plus gamma. So then the critical values of the superpotential are given by W hat A, and if I shift A by gamma, the critical value shifts by a period of alpha. So that's one way of seeing that there's no single-valued superpotential downstairs, because all the A plus gammas correspond to a single vacua downstairs. Here's a simple example. Take X to be the punctured complex plane with its standard Kähler metric, and alpha, the super one form, to be this one, where M is non-zero. So it's not exact. There's a single vacuum, a single zero of alpha, but if we go upstairs, then the deck group is gamma, upstairs meaning using the exponential map. And then if we pull back with the exponential map, W pulls back to W hat, which is exact. And the critical points of W hat form a Z-torsor. The critical values form another Z-torsor. And notice that if I shift A by N, the critical value of the superpotential shifts by the period of alpha. Other examples where this kind of thing occurs is the mirror of the CP1 model. Here's the alpha, again, X is C star. And in this case, you see that alpha has a quadratic polynomial in front. So there are two vacua. And it turns out there's one rank 1 deck group. Gamma is isomorphic to Z. I'll come back to this at the end of the talk if there's time. And other examples include Landau-Ginzburg models for knot homology. There's several in the literature. And then a very beautiful example is what I call Chern-Simons Landau-Ginzburg theory. So to formulate it, you choose a complex Lie group, GC, and a Riemannian three-manifold. And then I'll denote the corresponding canonical Landau-Ginzburg model by Chern-Simons Landau-Ginzburg of GC and M3. The target space, capital X, is the space of all complex GC connections on a three-manifold M3. So it is itself already infinite dimensional. The one form alpha is given by taking trace of the field strength squared, that's a 4 form, integrating over M3 to get a one form on field space. Formally, that's D of the Chern-Simons form. And the critical values of the Chern-Simons form are the flat connections. So in this theory, the vacua for this Landau-Ginzburg model on the real line can be identified with the flat connections on M3. Now, returning to the general case, it's useful to translate the Morse-Smale-Witten complex of superquantum mechanics into Landau-Ginzburg terms. So the approximate vacua in the superquantum mechanics were the zeros of psi, and they correspond to solutions of this differential equation, which I'll call the Zeta Soliton equation. Zeta here is a phase, and it will play an important role later. So similarly, the flows in the superquantum mechanics correspond to solutions in the Landau-Ginzburg language of this partial differential equation, which I'll call the Zeta Instantan equation. So this is an equation in the x tau plane. Tau is Euclidean time. And you see it's a deformation of the Cauchy-Riemann equation. In the math literature, it's often called the Witten equation, but there's so many Witten equations that I call it the Zeta Instantan equation. Now, let's look at the soliton complexes for the superquantum mechanics with calligraphic M and this psi in the case where D is the real line. So the Zeta soliton equation needs boundary conditions, and physically the right boundary conditions to put is a choice of vacuum of the Landau-Ginzburg model as x goes to minus infinity and x goes to plus infinity. So we'll call those vacua phi I and phi j. Once we've made that choice, we have a Morse-Smale-Witten complex. I'll call it the Soliton complex, Rij. As a vector space, it's just the linear span of now approximate ground states in this quantum field theory. So these are functionals, and they're built on each by quantizing around the classical solitons, phi ij of x. So you can calculate the fermion number of these ground states. It's given by an eta invariant of a certain Dirac operator, and then Qij counts Zeta instantons. When there are twisted masses, there's an interesting new wrinkle. There's something called flavor charge. So you see, if you have a classical soliton, phi ij of x, then it maps the real line to a path in the target space, capital X. And the path begins at x equals minus infinity at phi I, and it evolves at x equals plus infinity to phi j. So I'll denote the relative homology class of this path by gamma ij. So gamma ij is a relative homology class of a path going from phi I to phi j. And so it sits in capital gamma ij, which is the space of all paths in x from phi I to phi j considered up to homology. Now notice that we can add these kinds of relative homology classes. If we have a path going from I to j and j to k, we can compose them. And so we can add these charges in this sense. In particular, if the beginning and endpoint is the same, there's an abelian group structure on gamma ii, which is therefore isomorphic to gamma. And in general, gamma ij is a gamma torsor. So our soliton complex, Rij, is graded by the gamma torsor, gamma ij. Each of the components is itself a chain complex. And if we take the Euler character of that chain complex, trace minus 1 to the f, if you like, then that is the definition of the BPS index associated with the charge gamma ij. The central charge of these solitons, z gamma ij, is the integral of the one form alpha on this relative homology class gamma ij from phi I to phi j. This generalizes the standard expression, which many of you probably know, in the case when alpha is exact, where you can express the central charges Zij as the difference of the critical values of the well-defined superpotential downstairs. But if they're twisted masses, then there's no well-defined superpotential, and you have to talk about the Z gamma ij's. Indeed, if I shift gamma ij by gamma, then Z gamma ij shifts by the period, the gamma period of alpha. And a qualitatively new feature that occurs when you have twisted masses is that now you can have interesting solutions of the Zeta soliton equation where the boundary condition has the same vacuum on the left and the right. So phi of x goes to phi I on the left and the same phi I on the right. And when alpha is not exact, there can be non-trivial solutions. The image of under the soliton, II type soliton, can be a non-trivial closed curve in the target space X, and it can have a non-trivial period. And so the MSW complex for type II can then be non-trivial. And so then looking ahead, the main new ingredient in categorified wall crossing with twisted masses involves Fock spaces constructed from these complexes of periodic solitons. That's the main new message, the main new idea in the work that I'm doing with Hassan Khan. Now, speaking of wall crossing, let's recall a little bit about wall crossing when alpha is just exact. So in the case where there's a superpotential, you can consider a homotopy of the data that's used to define the quantum field theory, a continuous family of quantum field theories as a function of the control parameter S. And then you have soliton degeneracies, which now are just defined by a pair of vacua I and j. You don't need to have the gamma ij's. Mu ij of S. You might guess it being an Euler character would be constant, but surprisingly, it's only piecewise constant, as was discovered by Ciccati, Fenley, Trilogator, and Vafa in the early 90s. The jumps happen when two central charges become parallel. The Ciccati-Vafa wall crossing formula tells us exactly how these BPS degeneracies jump. The recent work is aimed at forming a categorified Ciccati-Vafa wall crossing formula, and the aim here is to describe how the homotopy equivalence class of Rij jumps. So I explained to you what a homotopy equivalence class of a chain complex is. Now, implicit in this statement is the claim that the homotopy equivalence class of the soliton chain complex is physically meaningful, so this is even a well-posed question. And moreover, that it's interesting, that is, that the homotopy equivalence class of Rij is a non-trivial refinement of the BPS index mu ij. Now, it's often said that the only thing we can hope to compute exactly in interacting non-integrable quantum field theories are Witten indices. For general X and W, these Landau-Ginzburg models are interacting and non-integrable. So what we are doing here has definite tension with that standard folklore. We're going beyond BPS indices here. But first, I should tell you what is the wall crossing formula, and I'll tell you the wall crossing formula in the most general case with twisted masses. So to formulate it, we introduce the vacuum groupoid algebra. So what that is for each flavor charge or relative homology class, little gamma ij, we introduce a variable, x sub gamma ij. And the multiplication is defined by saying I multiply two x's, and it's 0 if the paths do not compose, and it's x of the composed path if they do. So now, for every flavor charge, gamma ij, we introduce what's called an S factor, 1 plus the BPS index for that gamma ij times x gamma ij. And for all gamma, we introduce a K factor, which is a sum over the vacua of a Fock space character associated with the periodic solitons times x sub u sub I, where u sub I is the additive identity in the abelian group gamma ii. Then what we have to do is we have to choose a half plane in the complex plane, and we form this quantity S of h. It's the product over all charges such that the n equals 2 central charge lies in that specified half plane of the corresponding S and K factors. These factors do not compute, so I have to tell you how to order the product, and the rule is that you order them by the phase ordering of the n equals 2 central charges, the capital Z's. So the capital Z's, as you go along from left to right, you order the factors so that the capital Z's are rotating in the clockwise direction. Now the wall crossing formula says that this S of h is invariant provided no BPS rays either enter or leave that half plane as you vary your parameters. So it's very similar to the mathematics of the so-called 2D 4D wall crossing formula. Okay, so now to categorify this wall crossing formula, we think about branes. And specifically, we're going to be thinking about algebraic structures associated with branes. And the basic idea is that the homotopy class of the category of branes is invariant. So let's work up to that idea. So first of all, what's a brane? We have a 1+1 dimensional quantum field theory. And for definiteness, I've chosen the half plane to be the right half plane. So the spatial domain is a half line beginning at x equals x naught. And a brane is just a boundary condition for this quantum field theory. Now, there are very special branes called Lefschetz thimbles. So you choose a half plane and a phase, and then for each vacuum phi I, there's a canonical Lefschetz thimble Ti. So in the case of the right half plane, I can tell you what the support of this brane is. You simply consider all initial conditions phi of x naught so that there's a solution to the Zeta Soliton equation where phi of x naught evolves as x goes to infinity to the vacuum phi I. And a set of those initial conditions defines a submanifold of capital X. And those are Lagrangian subspaces, and they provide nice supersymmetric boundary conditions. So a very simple example is this one. Let W be a half phi squared. There's one vacuum, phi I equals 0. The Zeta Soliton equation is so easy, we can solve it exactly. And there are two branches of solutions, the plus and minus branch. Now, if we want the value of phi of x to evolve to phi equals 0, phi I equals 0, as x goes to plus infinity, we choose the negative branch. And then the phase of that solution at x equals x naught is fixed up to an overall real constant. So the possible initial conditions form a straight line in the complex phi plane, and indeed that's a Lagrangian submanifold. And similarly, you can do this for any half plane, for example, the left half plane. So now when we have these Lefschetz thimbles, these special branes, we can talk about boundary operators that potentially change the boundary condition. So again, you choose a half plane and a phase, and you let R hat ij be the vector space of local boundary condition changing operators between two Lefschetz thimbles. So I'll denote those boundary operators by a green square like this. So here's a boundary condition changing operator from Lefschetz thimble Ti to Tj. And because these don't break supersymmetry, R hat ij is a chain complex. In fact, it's much more. If I sum up over all the vacua, R hat ij is an algebra. Because if I have a boundary operator of type ij and another one of type jk, I can collide them and get an operator of type ik. Because of supersymmetry, there's no singularity in the OPE, so I just define a linear operator, rho 2, from R hat ij tensor R hat jk to R hat ik. And in fact, the sum of the R hat ij's has higher operator products, where I simultaneously collide n boundary operators to a single boundary operator. I'll call that rho n. And I can even include n equals 1 here, and then rho 1 is just the supersymmetry operator, the differential. Takes one operator to one operator. So this sum of R hat ij's is what's known as an A infinity algebra, which means the following. Imagine I take k successive boundary operators and I collapse them using rho k to a single operator. And I collapse all the remaining operators to a single operator. Now I look at all successive sets of k boundary operators and I sum over all k, and I sum with suitable signs and impose that the total sum is 0. Those are quadratic relations on these generalized operator products, and those are called the A infinity relations. And the claim is that in this Landau-Ginzburg model, these boundary operators satisfy, these operator products satisfy these A infinity relations. And the way you prove that is via something called the Web Formalism, which was developed with Gaiato and Witten using, in the case when alpha is exact. So you construct these multiplications using pictures like this, and in a few screens, I'll say exactly what this blue dot actually means. So there are two key papers for the Web Formalism, the paper I wrote with Davide and Edward, and then there's another important paper came out subsequently by Kapranov, Kontsevich, and Seubelman, where they took these webs and they looked at the dual polygons. And interestingly, they had a generalization of the formalism to higher dimensional polytopes. And as far as I know, there isn't a physical interpretation of that higher dimensional construction of theirs. And that's an interesting open problem. Now, people tell me that not many people have read this paper. And they tell me they can't read the paper because it's 430 pages long. But there's another paper that we wrote at the same time that concisely summarizes the main ideas, and it's only 51 pages. So you need another excuse. Anyway, A-infinity algebras generate these chain complexes. And just as there's a notion of homotopy equivalence of chain complexes, there's a notion of homotopy equivalence of A-infinity algebras. I won't give the technical details here. But it extends the notion of homotopy equivalence of chain complexes. And it says how the operator products are related to each other. Categorical wall crossing will involve the homotopy equivalence of these A-infinity algebras. It's actually very convenient and equivalent to formulate it not as an algebra, but as a category. So again, I'm still working when alpha is exact. So we choose a half plane and a phase, and then the objects in our category are thimbles, and the Hom spaces between the two thimbles is the space of boundary condition changing operators, r hat ij, provided the n equals 2 central charge, zij, lies in the space specified half plane. When I equals j, it's the trivial complex, and when I is not equal, and when zij is not in the half plane, the Hom space is just 0. Importantly, the r hat ij's, the boundary condition changing operators, can be written in terms of the Soliton complexes. And the formula is the following. Let E sub ij be the elementary matrix with a 1 in the ith row and jth column. And so now we make a matrix of complexes. R hat, capital R hat, is a matrix of complexes. So the matrix element in the ijth position is the complex R hat ij. The claim is that that's a product of simpler elementary factors which are made out of the Soliton complexes. So here you have Z, the trivial complex, times the unit matrix, plus Rij times Eij. And we take the product over pairs ij so long as Zij lies in the specified half plane. Now, these matrices on the right don't commute, so we have to order this, and we phase order that product. So now if you expand out the right-hand side, you discover that r hat ik is equal to rik plus rij tensor rjk, and so on. And you can associate pictures with each of the summands of the right-hand side. So for the first one, rik, we have a line parallel to zik going into the half plane. For rij tensor rjk, we have a line parallel to ij, a line separating vacua I and j parallel to zij, and another one, j and k, parallel to zijk. And so it goes. So in general, the summands correspond to sequences of central charges with successive vacua, whose phases are clockwise ordered and lying in the half plane H. Okay, now r hat ij is expressed in terms of these Soliton complexes. The Soliton complexes are complexes, they have a differential, and so automatically r hat inherits a differential from the Soliton complexes. But that is physically the wrong differential because it misses important instanton effects. The instantons have to do with solutions of the zeta instanton equation. Here again is the zeta instanton equation. And it has to do with solutions that obey what are called domain wall junction boundary conditions, or FAN boundary conditions for short. So these are boundary conditions in the x plus I tau plane, and here's an example. So in angular sectors, the Landau-Ginzburg field phi has to go to one of the vacua, phi I, phi j, and phi k. The angular sectors are separated at infinity by rays parallel to the n equals 2 central charge, zij, zjk, zki, and so on. And then a classical soliton, phi ij of x, tells us how, out at infinity, the field evolves from phi I to phi j across this ray. So notice that this picture here, which I'll call a fan of solitons, notice that this only makes sense if the central charges are clockwise ordered. Those boundary conditions might seem pretty exotic, but in fact they were studied over 20 years ago, and even exact solutions were found. So we could imagine trying to count solutions of the instanton equations with these boundary conditions. So if we have a fan of solitons, phi ij, phi jk, phi ki, we can consider it as a vector in this cyclic tensor product of soliton complexes. And if we count solutions, that defines what I'll call an interior amplitude. Now, if we sum over all such cyclic products of soliton complexes, we get a space I'll call RC, which it turns out has another interesting algebraic structure called an L-infinity algebra structure. It's very similar to the idea of A-infinity. And if you count the solutions of these, the Zeta instanton equation with these fan boundary conditions, you count those all up, that defines what's called a Morey-Cartan element in that L-infinity algebra. And that's a big generalization of that broken flows identity on the instanton numbers I mentioned before. So now we're ready for categorical wall crossing. First, in the case where alpha is exact. So the basic idea of categorical wall crossing is that if I have a homotopy of the basic data that defines my quantum field theory, so a continuous variation of the parameters that define my quantum field theory, then the corresponding A-infinity algebras of A-infinity categories of branes are homotopically equivalent. And that's strong enough to tell us how these soliton complexes, Rij, change up to homotopic equivalence. So here's the standard Chukkati-Vafa type situation. So in the complex Z plane, I've plotted on the left the central charges. And then there's a boundary, and as the parameters move, the central charges move, and you can imagine the Zij and the Zjk sweeping through the Zik. And that will happen at a real codimension 1 wall. So on the other side of the wall, the clockwise ordering of the phases has changed. And under these, this is the kind of situation in which the IK soliton spectrum will jump. So to say how the soliton complexes jump, we recall a definition from homological algebra. If F from C1 to C2 is a chain map, then the cone on F is the new chain complex, where I take the sum of the two vector spaces, and F is like an off-diagonal term on the differential. So now we can use this interior amplitude together with a contraction. The contraction exists because of CPT, and it maps Rij tensor Rji back to the ground field or to the integers. You can do all this over the integers. And so together those data define a chain map from Rik to Rij tensor Rjk, and that corrects the naive differential by adding an off-diagonal component to the differential on R hat Ik. So here in this Chukkati-Vafa type situation, on the left, we have Zeta instantons of this kind, and they define a chain map when we count up the number of solutions. On the right, we have Zeta instantons of this kind, and they define another chain map going the other way. And then the solution of the wall crossing constraint says that up to homotopy equivalence, the soliton complex of type Ik on the right is the cone of the soliton complexes on the left, and of course it's a symmetric relation. And conversely, if the categories are homotopically equivalent, then the soliton complexes are related by this cone construction up to homotopy equivalence. So if you look at this formula here and take Euler characters, you recover the renowned Chukkati-Vafa wall crossing formula for the BPS degeneracies. And this is the categorification. So I like to call these Chukkati-Vafa cones. And so then the question is, how do they generalize to the case with twisted masses? So I have 11 minutes. Let me say a few words about that. So this is the work in progress with Hassan. So a key definition is that a cyclic fan of charges is a cyclically ordered set of these flavor charges, so that the phases of the central charges, Z, are monotonically decreasing, that is, are clockwise ordered. The new ingredient here is that the successive central charges can be parallel. So we would say a fan is irreducible if all the vacua are always changing, and then the n equals 2 central charges, generically, will always be changing. So the phase is strictly decreasing. In that case, if we take to this picture, we would associate the cyclic product of soliton complexes. And if we sum over all of these cyclic products of soliton complexes, we have an L-infinity structure, and the old formalism applies. But the new element here is that we can have cyclic fans of charges like this, where the vacuum doesn't change. So we have a ray separating vacuum I1 from I1, and to that we might have a whole sequence of parallel central charges. Now, how do we represent that? To represent that, we introduce graded Fock spaces on R gamma JJ. And so if we have a picture like this to this line that separates vacuum J to J, we associate the tensor product of all the Fock spaces on periodic solitons whose central charges lie in between. So now if we sum over all the irreducible fans and insert the associated Fock spaces of periodic solitons, we get a picture like this. So here, this is from Hassan's thesis, this picture. In the case of 3 vacua, ordinarily without the periodic solitons, we would just associate Rij, Rjk, Rki, but with the periodic solitons, in between those, we insert Fock spaces of periodic solitons. And our conjecture is that this has a natural L-infinity structure associated with generalizations of these webs. And we have checked this in special cases. Similarly, you can go on and talk about the A-infinity category of branes. For R hat ij, you sum over all half-plane fans with Fock spaces of periodic JJ solitons inserted between the factors. And the conjecture is that R hat together with RC has the structure of an LA infinity category that is also known in the math literature as an open-closed homotopy category. So going back to the mirror of CP1, where X was the punctured complex plane and alpha was this one form, we had 2 vacua and a rank 1 deck group. And if you choose H to be the upper half plane in this figure, then the possible central charges would typically have a pattern like this called a Peacock pattern. So they accumulate on Z gamma. So now the new kind of wall crossing that you have with twisted masses happens when Z gamma ij when Z gamma ij is parallel to Z gamma, then an infinite number of rays cross through each other. Okay, so in this case, the R hat would be, which is a 2x2 matrix of complexes, would be an infinite product of these elementary factors, and then the new point is that we would insert Fock spaces of periodic solitons in between, in the center, corresponding to that ray with the parallel to the period Z gamma. Okay, I have a few minutes to talk about the last topic, which is the relationship to 3-dimensional supersymmetric quantum field theory. As I said, this is work with Hassan, Davide Gaiotto, and Fei Yan. So our motivation here was a recent striking conjecture by Garofalidis, Gu, and Marino. And they observed a relation between the 3-dimensional index. So that's a version of the Witten index for 3-dimensional quantum field theories, capital T. So we have a trace over the Hilbert space of that 3-dimensional quantum field theory, capital T, and it's trace -1 to the F. And if and in these theories, there are various global symmetry operators, R, J3, and so on. So we introduce fugacities, Q and X. And so we have some power series in Q of X. Now, the theory in question here for the GGM conjecture is that the theory T is what's called a class R theory associated to a hyperbolic knot complement. And I'll say more about what that means in a slide or two. And so they observed that these three-dimensional Witten indices, on the one hand, are the same as Stokes matrices associated to thimbles in complex Chern-Simons theory on that three-manifold MK, which is a hyperbolic knot complement. And so it was a very striking and somewhat mysterious observation. So we've given it a natural context, and we state a conjecture about Kapustin-Witten equations, which implies the GGM conjecture. Later on, we found out that that conjecture had been stated before by Viktor Mikhailov for very different reasons, so we're giving new evidence for Mikhailov's conjecture. Okay, so what is this theory T of M3? Very briefly, you take the six-dimensional 2-0 theory, and with a suitable twist, you compactify it on a three-manifold M3. And what you get, since 3 plus 3 is 6, what you get is a quantum field theory in 3 dimensions called T of M3. Now you could put that quantum field theory on a three-dimensional space-time, which is a cigar times time, and then with another twist, you can identify this Witten index with the trace over the Q cohomology of the local operators at the tip of the cigar. But the cigar has this nice U1 isometry of rotation, so you can Kaluza-Klein reduce with respect to that isometry to get a Landau-Ginzburg model on a half space. It's just a half space because the isometry is a fixed point at the tip of the cigar. And so at the tip of the cigar, so there's a boundary condition, I'll call it B cigar in this Landau-Ginzburg model. And the Q-closed local operators correspond to the boundary operators on B cigar. So this Witten index can be thought of in a Landau-Ginzburg type way, 1 plus 1 dimensional, as the trace over the Hom space between two branes, B cigar in itself, of minus 1 to the F times fugacities raised to various global symmetry operators. Now, what is this Landau-Ginzburg model? Well, you see, I just told you that we can take the 6D model, compactify in M3 to get T of M3, reduce on U1 to get a Landau-Ginzburg model, but we could, because of supersymmetry, also do it the other way around. We could reduce on U1, and then famously from 6D20 theory, you get 5-dimensional super Yang-Mills theory on M3 times the half line, R plus times R time, and then you can reduce that on M3, and now it's a straightforward exercise to show that what you get in 1 plus 1 dimensions is this Chern-Simons Landau-Ginzburg model I described before. So these are the same, and this B cigar is a boundary condition I'll call B num. So B num is related to the Kapustin-Witten equation. So if I Kaluza-Klein with respect to this isometry, I get 5-dimensional super Yang-Mills. And the BPS equations, as Witten studied this situation, and the BPS equations are the Kapustin-Witten equations, which are equations for a complex gauge field, curly A, on the 4-manifold M3 times R plus with the following boundary conditions. As Y goes to 0, the imaginary part of the gauge field has a simple pole with a residue proportional to the dry bind of the 3-manifold, and the real part is the spin connection. Here I'm taking SL2C. I have 2 minutes, and I will try and finish up expeditiously. So now that we were thinking in terms of Landau-Ginzburg models, we can expand this NOM boundary condition in terms of Lefschetz thimbles. So the vacua of the Chern-Simons Landau-Ginzburg theory are flat connections. And so, as I said, for each of the vacua, there's a Lefschetz thimble. So for each flat connection, there's a Lefschetz thimble. And then B nom can be expanded in terms of that. And the Kapustin-Witten equations with AY equals 0 are just the Zeta Soliton equations. So this Chen-Peyton complex is, again, an MSW complex for the Kapustin-Witten equations with non-boundary conditions at Y goes to 0, and A goes to the flat connection sigma I at Y goes to infinity. Okay, so now if we look at this, this character, then we can expand B cigar or B nom in terms of Chern-Simons thimbles. And now it's a fact that the trace over the Chern-Simons thimbles is the Stokes matrices for Chern-Simons thimbles. So we're very close to the GGM conjecture, and we now specialize to the hyperbolic knot complement. And among the flat SL2C connections on a hyperbolic knot complement, there's a distinguished one, which corresponds to the complete hyperbolic metric. And so the main conjecture is that these Chan-Payton spaces, or the solutions to the KW equations, are trivial unless you have the complete hyperbolic metric out at y goes to infinity. That's Mikhailov's conjecture. And what we're saying here is that it explains very nicely the GGM conjecture. Now, 2 more slides. This leads to a very interesting generalization. Suppose L is a link inside the 3-manifold M3 and it's colored by representations of SL2. Then Witten taught us how to modify the non-boundary conditions of 5D super Yang-Mills by including what's called an 't-Hooft line. And that corresponds in the Landau-Ginzburg language to a brane B of L, which up to homotopy equivalence only depends on the isotopy class of L in M3. So finally, our final conjecture is that the homotopy equivalence class of the A infinity category of branes on the Chern-Simons-Landau-Ginzburg model is a 3-manifold invariant. And if I consider the Hom spaces from B of L to itself, that is an A infinity algebra, and considered up to homotopy equivalence, and it's a new colored link invariant. So to conclude, sorry, I'm 1 minute over, using the framework of GMW, we derived a categorified version of the Cicciotti-Vafa wall crossing formula. The framework can be extended to the case with twisted masses, and here there are qualitatively new features, for example, involving Fock spaces of periodic solitons, and other new features that I didn't get to talk about. And a circle of ideas can be applied to the Chern-Simons-Landau-Ginzburg model to give a natural framework for interpreting a striking conjecture of GGM, and moreover suggests potentially new colored link invariants. So thank you for your attention, and sorry to go over.
Okay, so thank you very much for this interesting talk. Yeah, I invite questions from the audience, first in person and then online. So if anyone has questions.
So thank you very much for the interesting talk. And I just wanted to mention, since we're in a mathematical physics conference, in mathematical index theory, one needs some continuity estimates in order to justify homotopy invariance. And is there any way in these models to understand how to do that?
Is that Arthur?
Yes.
Yeah. Let me make sure I understand the question. So, right. So in index theory, we study something like Fredholm operators, and then the operator topology is important. I agree.
So how do you know that the beautiful picture you outlined actually applies to the quantum field theory?
Well, okay. So, I mean, I think I gave a pretty rigorous definition of the complex. Now, and you can take its Euler character. So, okay, I think I'm still sharing so I can show. Now, what I think you're getting at is that these BPS indices should be thought of as perhaps indices of some operator, some kind of Fredholm operator, or something like a Dirac-Ramond operator. And in fact, I think, Arthur, you did work on stuff like that. So let me go back to the very beginning. While I'm getting there, I as a more general, here we are. Let's see. There we go. Okay. So this is the key definition of the soliton complexes. And I believe there's, okay, so I believe, yeah, so you're asking, so you have to put in a topology on the operators in order for the index to be constant under changes of parameters. And you can probably interpret these BPS indices as indices of an operator in the quantum in the quantum field theory. Something like, it's going to be a supersymmetry operator, so it's going to be something like a Dirac operator on loop space. And so you'll have to get a grip on, well, I mean, there is rigorous work on the elliptic genus, right? So you're going to have to get a grip on the where your Dirac operator on loop space, what kind of algebra of operators that's living in, and what kind of topology you put on that. And the surprising point, of course, is going to be that the index is not invariant under continuous deformations of parameters that define the problem. That's the wall-crossing phenomenon. That's what's so surprising. So my understanding, and there are other examples where I can make this quite precise. My understanding is that what's going on is that you have a Fredholm operator which fails to be Fredholm at these walls of marginal stability. So there are examples. So for example, in four-dimensional quantum field theory, you can formulate BPS states semi-classically in terms of quantum mechanics on a moduli space of monopoles. And then the operator in question there is the Dirac operator on the moduli space of monopoles. And now we're on good, solid mathematic ground, because we have a Dirac operator on a well-defined finite dimensional space, and we can talk about it as a Fredholm operator and so on. And there, the wall crossing really happens when that operator fails to be Fredholm. Here we have a Dirac operator on loop space. And Arthur, I thought you had done work on making that kind of stuff rigorous, and I also
I did some
work.
work a long time ago on problems not as beautiful as these, but much simpler ones. And just, I'm wondering, the problems I worked on were two-dimensional, where you could actually do estimates. And
No, but it's exactly, it'll be very similar. These are 1+1 dimensional quantum field
but
theory.
yes, but is there some set of literature where I can go and read about this, where the estimates are actually done?
Oh, I don't think anybody's done, oh no, okay, that's the question, okay. No, nobody's done that. No. I mean, yeah, so to put it into that kind of framework, one would be studying the supersymmetry operator on this chain complex, and that's some kind of, as I said, I mean, I'm just repeating myself, that's some kind of analog of a Dirac operator on loop space, and then you're taking its index.
So, yes, I understand the classical picture, and it's very beautiful, and I'm wondering how to fit it into the quantum field theory.
Nope, Arthur, this is quantum field theory. The psi of this psi is an approximate ground state for doing the quantization of the quantum field theory around the classical soliton phi ij of x. So phi ij of x is a classical soliton, and then that defines the soliton sector of the quantum field theory. It's a sector of field space, the ij sector, and we can now do semi-classical quantization around that. Right. And I don't know what's been done rigorously about so that's a good question. That's more like the kind of question I would ask you. So if I have a quantum field theory and I have some soliton sectors, you know, we have a picture of semi-classical quantization around the soliton sector, right? Around the soliton. So the soliton is the classical ground state, and then there are quantum fluctuations in that sector of Hilbert space. And I don't know what's been done rigorously in that context. But that's the part of Hilbert space of a 1+1 dimensional quantum field theory we're working in. And now there's a subspace of approximate ground states of that Hilbert space. And there's this operator on that subspace, which is given by the unbroken supersymmetry.
Yeah, but then you also referred to the three-dimensional theory and this recent
So
conjectures.
the three, yes, there are connections to the three-dimensional theory, as I explained very in a lightning way at the last 4 or 5 minutes of the talk. So that's much less rigorous. I mean, it would be fantastic if something more concrete can be made. That's actually one of the virtues of bringing it down to 1+1 dimensions, where we have something really concrete. We have a Landau-Ginzburg model. We have an action. We have, it's just quantum field theory in 1+1 dimensions. It's interacting quantum field theory in 1+1 dimensions, but there's an action. And so that's the virtue of speaking that way. But, you know, even by physical standards, there isn't a definition of the 2-0 6-dimensional theory. So
sorry,
that is a huge open problem.
I think we have to defer the discussion to a more private setting now, because there's the next talk coming up.
Okay.
So thanks again to the speaker.
Thank you. Let me see.